little bit about our presenter today. It will be Frode Jakobsen. He's also presenting here for Denmark. Ask has a PhD from the Copenhagen University, and he's also the co-founder of QI and is the R&D manager. I will now hand over to Ask. Please go ahead, Ask.
Thank you, Anders. Hello, everyone. I'm very excited to give you this deep dive technical introduction to our DPI technology. It was introduced to the market 2 or 3 years ago and has been received very positive by clients, and we're very happy to see that they're coming back with more projects. They see game-changing results with regard to resolution in the inversion products, better separation of overlapping phases, and robustness with poor land seismic. And I hope by the end of this webinar that I've convinced you from a technical standpoint the reason for the bold statements, but also highlighted some of the disadvantages of the method. Today, we'll see how DPI work on synthetic data, and there is no replacement for real data. But it gives us a controlled environment to demonstrate both that the method works, but also test important corner cases. But hopefully it will also give you a better chance of understanding the inner workings. The exciting thing is that it's fundamentally very different from classical workflows, where you in some optimization loop try to minimize the difference between seismic and some synthetics. And the output is also different. Directly from the seismic we get probability distributions, and this without a doubt raises the abstraction level when used in subsequent reservoir characterization workflows, for example. So, overview of today. We'll start by looking at some of the shortcomings of traditional workflows to motivate introducing probabilistic inversion in general, the computational challenges, and how DPI make it possible to do commercial size projects. And we do project sizes that can, for example, be multi-azimuthal data sets with up to 16 stacks containing millions of traces with thousands of samples in each. The title, going under the hood, refers to the key concept in DPI of a local likelihood function, and we'll show how they're constructed and get a feel for how they work when they're exposed to seismic. And finally, we need to go from the evaluation of these many local likelihoods and arrive at a probability for each phases, which is our ultimate goal. And before we get started, I would like to make the following point. Traditional deterministic inversion is a great technology that gives you actual physical elastic attributes, integrating well-logged data, seismic data, based on physics in a very well understood workflow. And DPI is developed to address some of these disadvantages. And I hope by the end of today's webinar that you'll have a clear picture of advantages and disadvantages of the different methods. So let's dive into the problem of non-uniqueness. So let's just do a simple forward modeling exercise. To the left, the 2 leftmost tracks are identical and have the same elastic properties with no variability in the 5 defined phases. The cross plot shows the detrended data, and we clearly see 2 different trends. But when we do the seismic forward modeling, we see that they generate the same seismic. But the high frequencies are also missing. And to the left, you see 2 different phase sequences that give different elastic logs, again based on this cross plot. And we see that even though they're very different, we get 2 angle stacks that are basically the same, even though there are only 5 values allowed. And we see, for example, at 1.55 that we see one sand can be like a train of sands, and other differences at 1.65. And this is a problem, even in this case where we have no noise. But we could also have a set of logs with underlying phases logs that doesn't make sense at all, like for example hydrocarbon sands below brine sand. but also unrealistic combinations of the elastic logs if we were allowed to have any location in the crossplot and not restricted to these 5 locations. When we then add noise to the problem, we enhance this non-uniqueness. That's just based on bandwidth limits. When we add noise, it gets even easier to construct facius logs that are significantly different, but has the same seismic within the noise level. And this is traditionally handled by regularization. Find a slightly different problem that is well posed with one solution. And this biased solution effectively results in a smooth solution. And more loosely speaking, one can think of that solution as some average of all the solutions to the original problem. So going forward, we will focus on inversion or interpretation from seismic to categorical classes like facius or litho classes. So we go one step beyond elastic. The complexity can be staggering, as seen in this figure, but obviously it's of great importance to our clients. Therefore, after inversion, you will typically do some interpretation or some step to get facius or lithologies. And this step has its own set of problems. If we just leave out seismic for a second and assume that we have the perfect wireline tool that provides us with elastic logs like AI, and we are to classify based on the elastic logs only. And in this case, we have defined 3 phases: shale, hydrocarbon sand, and brine sand. When no variability or overlap, the problem of classification is easy, as seen in the leftmost figure. But unfortunately, nature does not always play nice and does not ensure that the categories of phases that we are interested in separates out nicely in elastic crossplots, where we feel at home and can do modeling. In the case of elastic variability, the 3 phases could be centered around some point and have some spread that makes the phases classes overlap, as seen in these colored blobs. Now there's not a single solution, and not surprisingly, the problem lends itself to a probabilistic interpretation. But let's compare 2 different interpretations or solutions of the AI log. The one to the left is much more likely, since the brine and hydrocarbon sands are closer to the blob centers, so to speak. But we can't rule out the solution to the right, only say that it's less likely. But if we introduce spatial information, we can exclude the solution to the right, giving larger weight to the solution on the left in the set of all solutions. This combination of crossplot, whereabouts, and spatial information that guides us around the colored blobs with depth is at the core of DPI. If we now get seismic back into the picture, so now we have noise and we have realistic facius classes that overlap in the crossplot, things get complicated. In this figure, we have the ground truth to the right, and we have 500 solutions that fit the seismic data equally well within a realistic noise level. More later on how we actually generate these solutions. The figure clearly demonstrates the classic problem that a thin gas can look as a slightly thicker oil sand or a thick brine sand, which could lead to false positives and or missed opportunities, as indicated by the arrows. But it's important to stress that you can't just choose the best fitting solution, since that solution is most likely fitting noise and or is the result of some non-likely combination of elastic properties in the crossplot. However, it does motivate us to find the unique probability distribution that solves the problem. Instead of just finding one solution, then we find a probability distribution. So we get a well-posed problem and at the same time integrate this non-uniqueness into the solution. But before we do this, let's look at a high level on the classic workflows for getting facius lithologies from seismic data and some of its shortcomings. Sorry, just a glass of water. The classic workflow is to do a deterministic inversion and then feed that elastic result into a pointwise faceless lithology classification interpretation of some sort. And it could be some Bayesian scheme. And in the following slides, we will see visually the challenges in basically any classic two-step workflow. So if we start with the simplest case imaginable, each faces has again just distinct properties as seen in the red curves, where we see some synthetic observed data. From this, we can make synthetic generated angle gathers with some noise seen in the last track. And if we then do a deterministic inversion, we arrive at a result shown in blue. And one can always discuss if this result is good or how relevant this synthetic world is as compared to real data. But it contains all the typical problems. The inversion result is a smooth curve, and it over and undershoots, has side lobes effects, etc. Now, if we color code these inverted results with the true faces, it's smeared in the crossplot, making it hard to interpret the faces. And if we do maybe a little more realistic case where we overlap, where we have faces with overlap, we see that things are not getting simpler. Notice that some gas points could be mistaken for shale, and oil and gas are now quite overlapping. So in this setup, we have to work within the confines of the fundamental problem of overlap and the smooth deterministic inversion result. So what is lacking? In interpretation, we only look at whereabouts in the crossplot in a pointwise manner. Our results are not influenced by our neighbors, and we need to know something about our neighbors to exclude or downweight things that does not make sense. As we saw in the example of the synthetic wireline case, we could exclude something by looking at our neighbors. And ideally, we need to have control of all spatial dependencies in all the domains that are relevant: seismic, elastic, and the facies or rock domain. So the two-step workflow kind of lose track of this spatial dependence, and the smooth input make it difficult to handle thin beds, and it leads to high probability of unphysical events. So you get this Swiss cheese-like results where you go through a brine sand to get into a hydrocarbon sand, which does not make sense, and then you exit through a brine sand, or you want water contact or not. And for a real data case on this topic, at this year's EAG, there was an abstract where they compare traditional two-step classification to DPI in a challenging study with sub-seismic reservoirs, not sand reservoirs, interbedded with thin coals and shales. And the results showed that DPI was significantly better at predicting sands and coals, and the results were more continuous and had better extrapolation properties away from the well. So for a small digression, which actually originates from the medical imaging industry that is very far in the use of these probabilistic methods. And it really neatly demonstrates the advantages and disadvantages of a Bayesian approach on which DPI is based. So let's say we're in the business of detecting letters in text. The letters are formed by these structures of binary values representing black and white. We then have some measurement, some imperfect measurement that is contaminated by noise, which we can model as a Gaussian blur. Despite being very simple and linear with only one solution, in a noise-free case, it is ill-conditioned. So it's difficult to solve when there's noise. But we can replace the math of the original problem by a different problem that is constructed in such a way that for this value, for some large enough value of alpha, we have a solution, and we hope it makes sense. And this is an example of a regularization. The result is smoothly varying, and it makes a lot of sense, but it's still far from the original. But let's wish for a better resolution and the possibility of doing uncertainty analysis. Improved resolution does not appear by magic, but from adding information directly into the inversion problem. And we have a very strong notion that letters are blocking. So we have domain-specific knowledge, but how to use it in the inversion process. Okay, enter Bayesian equation or probabilistic inversion. Now we can restrict our solution space by a prior that promotes this blockiness. And in this case, it's the Ising model, well known from physics. And the solution is now a PDF, and we can find the mean, and we can find the variance, and we can draw realizations. And we can clearly see that the apparent resolution is much higher. And the funny thing is, we only need to add a small amount of blockiness to the problem, qualitatively speaking, to get the result. So the result is hidden in the data, and a little prior information can help make that solution drop out. And so there's some clear advantages as compared to the regularized solution, but the disadvantages and complexity are also significant. There's an explosion in computational burden. There's the problem of what prior to construct and how to construct it. And then there's the more abstract concept of working with a PDF instead of a single solution. So let's compare that with the faces inversion. As we can see here, there's a lot of similarities, but also some noticeable differences. The blur is different. We have multiple and not binary classes, and they are overlapping, and we have a two-model forward hierarchy. So we have the rock physics and the seismic modeling. So the next question is, do we have this domain-specific information like we saw in the previous slide concerning text that we can put to use in the inversion? And the good news is we have abundance of this kind of information that are typically underutilized in the inversion, and it kind of bridges the information from geology, geophysics, and reservoir engineering. Geology can have strong constraint on where phases exist and in which order. And from geophysics, we have all the fundamentals like fluid ordering. And if a field is known to be in pressure contact, one can have large certainty. One can with large certainty discount any oil sands below oil water contact, for example, if we take into account the uncertainty of the oil water contact location. So the idea is, at a very high level, is to infuse broad prior information with emphasis on broad, and then add the strong constraints of all the stuff we are absolutely sure of directly into the inversion. And by reducing the solution space dramatically, the solution buried in or hidden in the noisy seismic data should pop out at us. That's the hope. But it's important to stress that we want the data to speak, so it doesn't become a modeling exercise. So we have established that there exists prior information, and we know the Bayesian equations. So now we should basically just go to work and solve the problem. Analytically, it's kind of out of the question if we want to keep just a minimum of spatial information and want a high degree of flexibility on what models to use. And there exist some more brute force methods that should in theory always work, but they're extremely slow. And they have their own set of problems. But we'll see in the end, we actually use metropolis hasting, which is one of these slow methods, to actually check for the correctness of the DPI results in the end, because we do some approximations. More on that later. So from like a very high level, we embraced the framework that was set out in the paper by Ullum and Kolbjørnsen in 2016, where they developed this idea of a localized Bayesian one-step method. And the good news is that it retains important spatial information, and it's very has very few limits on what kind of models to use, assumptions on the models you want to use. It's easy to parallelize. And the key concept is a clever use of localization in all three domains, and then with some efficient approximations on top. So by localization, we mean that we only work with the part of the likelihood model that is the most relevant and contains most of the spatial variability. So that would be like phases, thickness distributions, disallowed sequences, like oil below brine, tracking, so generally tracking the movement around the crossplot, but also the blurring due to the bandwidth limited seismic and the signal to noise ratio and all the characteristics of the seismic noise. And all this is propagated directly into the final result in one go. It's also worth stressing that we only rely on local prior information. Geology tends to be very non-stationary, so to do a realistic global prior is not easy to construct, especially for a large complicated plate. But we only need to know some approximate prior locally, which is a great advantage. So how does DPI work under the hood, looking at the engine from a distance, so to speak? So let's say we want to find the phases probability at a given seismic grid point, indicated by the arrow to the right. Then, as you can see on the left seismic, we cut out a piece of seismic of approximately wavelet length centered around the grid point in question, and cut it out and insert it into this Bayes equation, this cartoon version of Bayes equation. The local likelihood of the seismic for that phases window, in this case, it's a window of length 7 with a sand at the grid point of the arrow. It's then multiplied by the prior probability for that phases window, which by Bayes equation is proportional to the posterior of the phases window. And this is done for many phases window, and indicated by this set of windows down here. A priori, some of these are more likely than others. And this is what we'll go into detail within the coming slides. But it allows us to integrate and marginalize out all but the center sample at the grid point. And this process is then repeated for all seismic grid points. So if we zoom in on the core equation, so by a window, we mean it's something that has an extent in the seismic grid, and its center means relative to some seismic, specific seismic grid point. In this case, it's a brine sand with 3 overlying grid points are shale, and the 3 underlying are some sequence of limestone, shale, limestone. And we can basically see the inversion, so to speak, by the reversal of arguments here. So we have a likelihood to the right, but what we want is the probability of a sequence given the observed seismic. So we can go through some cases to get a feel for this equation. So if there's a sequence that are not allowed a priori, like hydrocarbon sands below brine sands, or some geological ordering, the prior to the right is 0 and drops out of the whole solution. Because remember that an illegal sequence can look identical to a legal sequence on the seismic. And depending on the spatial model, some sequences are a priori much more likely than others, are much more, for example, rare than others. And these rare sequences will require more emphasis from the likelihood term by actually being present in the data to be boosted in the final posterior. And if we take the case where the signal to noise ratio is really low, like poor seismic, most sequences will have a similar likelihood. More or less anything goes. and the prior will dominate or stabilize the result. And it's vice versa for high signal-to-noise ratio. But all this is still very abstract, this equation or this cartoon equation. So there are some different questions that come to mind. How is this local likelihood model constructed? And how do we choose all these sequences in a structured manner? And how do we in the end get a probability at that seismic grid point in question? And that's what we will focus on in the coming slides. So if we look at building of the local likelihood, in this case rock physics likelihood, we basically, this is the brute force way of doing it, is that you for given phases window, you generate, let's say, 1 million short phasor sequences that are approximately 2 times a wavelet long, that all has the same sequence in the middle, indicated by this orange box you see. And let's say we generate 1 million. And visually we can clearly see that the shales are thick and the sands and limestones are thinner in this particular case. And there's also enforced fluid ordering. With the 1 million phases logs, we can then populate 1 million times 3 short elastic sequences using some sort of rock physics model. And statistically, these 3 times 1 million small logs will now statistically contain all the information from the spatial model, how the elastic properties change within a phasor sequence, and statistical dependencies between the elastic variables, AI, VPVS, and density, or whatever elastic parameters you favor. And this statistical information for this window can be encoded approximately by a multivariate Gaussian. And a Gaussian is parameterized by a mean, vector, and a covariance matrix. And then there's some tricks to be able to capture the non-Gaussianity of the rock physics likelihood. We do some tricks that are not important to understand how DPI works. But in the end, we do this procedure for many phases windows, and we end up at the end with a factory, so to speak, where we from an arbitrary phases sequence or window can construct a rock physics likelihood approximation. So it can spit out a mean and a covariance matrix. And you can see this in action here. So to see how it works, you can see to the left, we have some sequence, and then we put it into this factory we've built that can spit out a mean given that window, but also the covariance matrix. And the covariance matrix is difficult to show. So it's been, so here it's just indicated by the diagonal, the standard deviation, the square root of the diagonal. Then we can take our linear seismic model, and then we can look at what will be the mean and the covariance matrix for the seismic conditioned by this phases window. And that's what we see here in the dark gray, where we also see these bands of the standard deviation, the square root of the diagonal. So now we've seen how this machine works, so to speak. Let's now apply it to some data and see how it actually works. So in this case, we have 100% synthetic DPI result that would be our test bed for this. So we have a synthetic angle stack that's created with some wavelets on some reflectivity that's been calculated from the elastic contrast found from populating a lot of elastic logs using the rock physics model. So we have the ground phases truth out here to the right. And the resulting cross plots can then be seen here. And then we add some noise, which are significant, at least when you compare the shale to brine sand interface. In this synthetic case, we'll just assume a constant prior probability, having it much more likely to be shale or silt, and less likely to be a brine sand, and very unlikely to be any hydrocarbon sand. This seismic is then fed into DPI, and out comes the posterior in one step, where we go from the seismic to the facies probabilities. And to get a feel of how it works, we'll concentrate on 2 seismic grid points and see how the mechanics of these likelihoods are. So we'll concentrate on 82, where there's like a 50-50% chance of oil or gas at this big seismic event, and then some more dull case where we have this boring shale silt sequence that are dominated by noise. But we see that the results really downplay that there should be any sense there. So we have a facies window, and then we have this method of generating these rock physics likelihoods, and we can then take them to the seismic domain and get this seismic likelihood. And to be able to discern the seismic data in black, we have colored the mean and the standard deviation around it orange. And now we'll randomly try some interesting windows. So we start out with this very unlikely facies window of that it's all shale around that center point, and that's a priori very likely, but the data does not really support this because the seismic is really far from the mean. And then we can try different cases. We can see, could it be a small sand, a thin sand here in the center? And we can see that we still have a lot of wiggles that are well out of scope, well out of these orange bands. And then we can try something where we have something that's partly true around the center sample, but then it should have an overlying oil brine sequence. And this is also very unlikely, because you can see a lot of the black curve is not within the seismic likelihood function. And then we can test something that's pretty good. Now it's the true answer, but with oil instead of gas. And we now see that this fits much better. And then we can take the one that's spot on. And we see it fits, in this case, slightly better. So what I mean by spot on, this sequence is spot on with the ground truth. And in this case, it actually has the largest log likelihood, but there's no guarantee of this, of course. And it's only a slightly better likelihood than the one we saw previous. Then we can go to this more boring case where it's very dominated by noise, and more or less anything goes. As we can see here, if it's a shale sequence or a silt sequence, it's really not making a big difference. We can put in a thin sand, and if we look at the log likelihood, we will see that it decreases a little bit, but it's not very significant. But a priori, a sand is much more unlikely. We can then take some more. Could it be a thin oil sand? And now we see that on average this will have this larger wiggle, and we start to see that this will have a much lower likelihood. And we take something like a big gas sand, and we see it's completely off. So this is a very unlikely sequence. And then we can take the one that's spot on. So the conclusion is that by carefully watching the log likelihoods, then any shale sequence is quite likely. The brine sand is slightly less likely, but we see that it's downweighted because of the prior. So in the end, we end. So the sand is kind of silenced, so to speak. But now we have all these likelihoods, and we can see this is some sort of statistical matching in some sense. And in the end, we see that each of these sequences carry some weight based on how well the seismic fits how that sequence should look. So the next set of questions that comes to mind is, how do we choose these sequences? Because I just chose some random ones that I thought would be interesting. And we also know that the likelihood is only half the story. The spot-on sequence might not be the one with the best likelihood. And we don't expect one sequence to be the magic bullet, because we have to remember the non-uniqueness and the noise. And then finally, we also want to go to the probability at that specific point, integrating out all the other grid points. So for each phases in the problem, we generate a lot of phases windows conditioned on the phases center at the point, in this case, the yellow brine sand, as you see in this set, using the spatial prior model. And we do this for each phases. And notice that, for example, illegal sequences are not generated and are not part of the solution or the workload. And this conditional sampling idea allows us to oversample, which is crucial to get good accuracy. That the a priori rare phases are sampled just as much as the non-rare. And naturally, this effect is of oversampling is adjusted for, but it's very important to get good statistics also for the rare events, which we are typically looking for. And the larger the window, the more conditionals you need to get good accuracy. And we don't have to do this exhaustively, since the spot-on sequence for large windows are statistically not important, because any nearby sequence will probably add the necessary weight. Then this equation is then evaluated for the conditioned phases window, basically just evaluating the likelihood many times, because these sets can be big. And then after some realization or normalization, which basically end up being a counting exercise, we arrive at the probability at the center point. And this is the entire process that is repeated on all seismic grid points. So this is, so to speak, the DPI engine under the hood in a high level view. So as we saw, we do a lot of approximations here. We saw that we are localizing and we are also approximating. But we saw that there was a method that should give us the truth, so to speak, the true posterior probability distribution with no such approximations or local assumptions. And then we can build a synthetic test case, and we can then compare. We have the ground truth to the left. We can then compare the posterior of the Metropolis Hastings with the posterior of DPI. And the conclusion is that there is good agreement. So these approximations are well controlled. And this, I think, is a good example. If we just look at this example here, that converting from probabilities to most likely phases, you throw out a lot of information. So in this case, you can see we are kind of on the border of being either one or the other, a brine sand or oil sand or whatever the case is here. But if we just look at the most likely, we don't see this, that we're not sure, that the data doesn't give us enough information, or the prior gives us enough information. So that the technical short recap is that we've seen that we can go from gathers to probabilities in one step that takes all the spatial information into account from the different domains. And we've seen how we approximate the rock physics likelihood and reduce the problem to a manageable size. And we saw how these approximations work. And we can see that DPI is very robust because we simply evaluate very well behaved functions. And we have a Bayesian prior to stabilize the solution. And these nice mathematical properties are seen on real data to have positive consequences. So we've seen that we can resolve thin beds below tuning thickness and we can separate the challenging fluid phases. And since we do this simple evaluation of nice functions, we've seen that it's very robust and provide good results on challenging land data. And furthermore, we see that the results are continuous from trace to trace, not jumpy, which gives us confidence in the results. And in the DPI, we only use the well-log data for prior statistics. So we don't do a direct fit or interpretation directly to the well-log data, which we have shown with the real data gives us really good extrapolation properties away from the wells. And the flip side is that despite being a fast probabilistic method, it is still slow compared to traditional two-step methods, especially in compute time. And the method also requires a lot more communication with the client to find appropriate information that we can utilize. But this also makes it very interesting. Yeah, so I hope this gives an idea of how it works and some of the advantages as well as disadvantages. So thank you for your attention, and if you have any questions, don't hesitate to ask or get back to us with any questions or references. Thank you.